All right, ladies and gentlemen, so we're looking at this roller coaster. So we have our car gets pulled up to here. What kind of energy are we going to have up here at A? What do we think? Who's an idea? Who's a guess? What kind of energy do we have at the top at A when the car gets pulled up to the top?
Potential.
Awesome. We have potential energy up here, gravitational potential energy that is assumed based on the fact that we have a height. Anytime you see a height, we know gravitational potential energy has to be there. All right, what about as the car goes down? We're assuming no friction. So what about as the car gets down to B? What kind of energy do we have there?
Kinetic.
Kinetic energy. Awesome. Anytime there's movement, we have kinetic energy. What about at C? What kind of energy are we going to have at C?
Gravitational and kinetic.
All right, I heard gravitational and kinetic, and that is going to be correct because we still have a height right here. It's smaller than before, but we have that height. But the box or the car is still going to be moving as it gets up here, which means it's not stopping at the top, just like it did for part A, which means it has that kinetic energy because it's still moving. What about at D? What do we think?
Kinetic.
Kinetic, all right. Any other forms of energy?
Would there also be gravitational since it's above ground?
Exactly. It's not at the ground yet, so it still has that gravitational potential energy. And what about at E?
Just gravitational
All right,
potential.
gravitational potential because we're at a height. Everybody agree? Any other forms of energy there?
Kinetic also.
We still got some kinetic energy here because we're not at the same height as we started, which means there is some gravitational potential energy and there is some kinetic energy. They're still moving. This is what probably like if you're thinking about roller coasters, if you've ever been on a roller coaster, you kind of come to a slower, and then finally stop at the very end. So that is this part where we're coming to that stop, but we're not there yet. All right, so then the second half of that question did ask, what happens when we add friction back in? So let's add friction back into our problem and let's identify those forces starting back at A. What forces, or sorry, not forces, forms of energy. So let's start back at A. What kind of energy do we have at the top? Somebody tell me at least one form of energy at the top.
Gravitational.
Gravitational potential energy. Yep, it hasn't changed. We still have that gravitational potential energy, and this is the start of our roller coaster, which means we haven't done anything, so there aren't any other forms of energy to have. So because it's the start, we haven't done anything, there's no other forms of energy that could exist. What happens as we go to B?
There's kinetic energy.
There's kinetic energy, all right. Any other forms of energy there? Remember, we're adding frictions. There's something
Thermal.
thermal or heat or dissipated energy. So we have that Q. Because there's friction. Friction causes us to lose energy. When I say lose energy, it's losing from the system. So it's going somewhere else. It's getting transferred to a different place. It doesn't just disappear, which is where that thermal energy comes into place. So down here we have both. What about at sea? Who can tell me at least one form of energy at sea?
Kinetic potential and thermal.
Kinetic potential and thermal. Perfect. We have all three of them here. Because there's still friction on the cart. All right, what about at D?
All three again.
All three again. And what about at E?
All three again.
All three again. Perfect. All right, so this is probably a more realistic version of a roller coaster. We start out at the top of our track, and as soon as we get to the top, that chain that pulls us up to the top is going to let go, leaving us just with our potential gravitational potential energy to get us moving down the other side of this roller coaster, making us slow down a little bit because of friction, but we have that large kinetic energy as we come back up. The one thing I do want you guys to realize is as we keep going, this friction, so the friction here doesn't stop, which means our thermal energy or our dissipated energy, that Q, is only ever going to increase. And as soon as we start moving, that thermal energy comes into place, that dissipated energy comes in, and it just gets bigger every single time. So every time we get to a different point, it's going to be bigger until it gets to a very large number over here, which is the reason we come to that slower, almost stop like on a roller coaster before they hook us back up to that chain and actually stop us. We're slowing down as we get to that last point because of thermal energy or that dissipated energy, that Q. The other thing I want us to remember is that all of our energy that we start with a total up here. So this is our total amount of energy at the start of this problem at this roller coaster. This total has to stay the same the entire time. So our total is going to stay the same down here. It'll equal all of this all added together here. Our total doesn't change from down here. Our total is not going to change over here. The total never changes, only where the amount in each of the other forms of energy can change.